This is Jack Jackson. In this video we're going to talk about physical interpretations of the derivative in context. Now, you know, all this stuff about derivatives, we've looked at how we can see a derivative from a formula, from a table, from a graph. But what really makes this thing useful is how we can put it in a real-world context. You know, this is really cool stuff, and it's like a neat puzzle, neat mathematically. Mathematicians are going to get really excited about this stuff. But most of the rest of the world, if they want to see it put to use somehow. So let's start to look at how we might interpret the derivative in a real-world context. So the first thing we want to do is look about what the units would be. So most things, you know, have some kind of units like feet or inches or meters or seconds or degrees or something. There's some kind of units involved with it. Well, how do the units of f prime of x, the derivative of x, compare to the units of f and the units of x? Well, remember, if we use Newton notation, that's f prime of x, Leibniz notation kind of helps us remember where this thing comes from. df over dx is the Leibniz notation, and remember that's the limit as h goes to 0 of f of x plus h minus f of x over h. Of course, h is delta x, so we could also write the numerator as just delta f, the denominator is delta x. And sort of a simplified version of what's going on here is the last one, the limit as delta x approaches 0 of delta f over delta x. So what we really have here is just this good old slope formula, a difference quotient, which is just the slope, and then we take a limit. Well, taking the limit doesn't change the units. The numerator has units, whatever the output units are of the function, whatever the f units or y units are for the function. And the denominator has units too, the input or x, whatever the units are for that, that's the denominator. So the units of the derivative are the same as the units of that difference quotient, which are always fractional units. So, in fact, they're over the units of the numerator over the units of the denominator, and so what that is, it's the units of the numerator are the units of f, the output units, and the input units are the denominator. So let's look at a specific example. If we look back at where we started these notes, if p of x is a position in miles along a particular highway and t is the time in hours since some particular point in time where t equals 0, then the units of p prime of t are the units of p divided by the units of t. So, for example, in this example, they would be miles per hour, which of course helps give us an understanding of the derivative, which in this case is a speed, an instantaneous speed, or give it a direction as well, then a velocity. Let's also look at another way that will help us with derivatives. So, the first thing is knowing about the units can help us considerably understand what's going on. Now, look at what's happening in this graph. I've got a close-up view of a particular point on the graph, AF of A, and I've looked at some delta x, is h, and I moved over that red distance. Now, if I follow the tangent line and go up, if delta x is 1, so the red distance, delta x, or h is 1, notice by the slider, h is 1, then the slope of that line is the amount that line is going up when we go to the right 1. That's what the slope means. It's the amount of change in the line. So it's how much the tangent line goes up when we go up 1. That's the slope of the tangent line, which is the derivative. So the derivative can be seen as an actual physical distance on the graph, which is this black line distance right here between these 2 points here. So you go straight across to the right 1, and then however far you go up or down to get to the tangent line, that's f prime of A. Now, for that same delta x is 1, delta f then is how far you go up or down to get to the actual point on the graph. So this distance from down here up to this point here, the vertical distance from A up to f of A, this green line here, that distance is actually delta f when delta x is 1. That is f of A plus h minus f of A for h being 1. In other words, it's f of A, f of 1 plus h, or f of A plus 1. Maybe I'll be specific about that here. And so that is that vertical distance. So I want to point out, first of all, that these two things are not exactly the same distance, right? When we go to the right one, we don't necessarily go up the same amount on the graph of the function as we do on its derivative. However, I want to also emphasize that these two things, even though they're not the same, are actually quite close to each other. Recall that the derivative is approximately equal to the difference quotient when delta x is close to 0. And oftentimes we can think of delta x equals 1 as relatively close to 0, or close enough to 0 for many real-world applications to be a reasonable estimate. So, let's look at the algebra of what's going on here. The derivative is the limit as h goes to 0 of f of x plus h minus f of x over h, which is just another way of saying the limit as delta x approaches 0, delta x over delta x, delta f over delta x. So that is approximately the same as just the difference quotient, delta f over delta x, if delta x is close to 0. But delta f over delta x equals delta f if delta x is 1. So if we consider 1 close enough to 0, then we see that f prime of x is approximately the same thing as the delta f. So we're saying that these two distances, this distance here, which is f prime, and this distance here, which is delta f, are not the same, but you can think of them as close to being the same. And that gives us a nice way of interpreting this. Business people refer to this by the word marginal. Okay? So in business applications, we use this word marginal. So, for example, if the function is the cost function, some business textbooks will refer to the marginal cost as the additional amount of cost for manufacturing one more item above A items. In other words, it's the cost of making that A plus first item. Okay? Now, other texts actually use the word marginal for derivative, so the marginal cost is C prime of A. And we've seen those two things are not the same, but they're also very close to each other. So we're going to use one to approximate the other. In this class, we'll take the second version. We'll use the word marginal to mean derivative. So anytime you hear me talk about a marginal cost, that's a derivative of the cost function. Or marginal profit, that's the derivative of the profit. So we'll actually use it to be the actual derivative. But what we'll say is that is approximately the same as the actual change in the function by adding one more item to the input. So in general, we'll use the derivative at a point to estimate the amount of increase or decrease in the output if we increase the input by 1. So, and sometimes we'll do it the other way around. Sometimes we'll use the amount of increase to estimate the derivative. Essentially, we've been using difference quotients and symmetric difference quotients to estimate the derivative. Later on, we may switch it around where we use the derivative to estimate this amount of increase. So, let's see if we can put some of these ideas, these ideas of what we have, in context, and work in context. So I've got a series of real-world application problems where we see if we can apply these basic ideas. So notice that when we're asking about the sign of the derivative, whether it's negative, 0, positive, we're asking about the direction of the original function, decreasing, stationary, or increasing. When we are asking about the sign of the second derivative, let me be sure we put first up here just to emphasize that. Whether it's negative, 0, positive, what are we asking about the original function? We're asking about the concavity. Whether it's concave, down, neither up nor down, which could be possible inflection point, or whether it is concave up. Okay, keep that in mind along with this idea of the the marginal idea of the local linearity and our units as we're working through these problems. Okay, so here's our first example. Let G of t be the height in inches of Amelia Earhart, who was one of the first famous women to fly airplanes, famous pilot, and t is the number of years after her birth. So see if you can answer these questions. What are the units of G prime of t, and what can you say about the sine of G prime of 10, and what about the sine of G prime of 30? So I want you to think about this, get an answer, and then come back and I'll go over the answer. But I want you to try to do it on your own first. You'll learn a lot more if you'll do it that way. So press pause now. Well, the units of G prime of t are the units of G divided by the units of t. So since G is measured in inches, t is measured in years, the units of G prime of t are inches per year. Per means divided by. So inches per year. So what is G prime of t measuring? It's measuring how fast she is growing t years after her birth in inches per year. So G prime of 10 is the instantaneous rate of growth right on her 10th birthday. So notice G prime of 10 is positive because since we're asking about whether the sine is positive on G prime, we're asking about whether the original function is increasing or decreasing at that point. Well, when she's 10 years old, she's still growing in height, so G prime of 10 is positive. If G prime of 10 happened to be 4, then that's saying at that point she's growing at a rate of about 4 inches per year. We don't know what it is because it didn't tell us, but we do know it's positive because we know a 10-year-old girl is going to be growing in height. On the other hand, G prime of 30 is 0. Because at 30 years, she is neither increasing in height nor decreasing in height. She's leveled out, and the function g is actually constant at that point. Okay, let's try another one. So we've got an economist is interested in how the price of a certain commodity affects its sales. Suppose that a price of P dollars, a quantity Q of the commodity is sold. Okay. Now, think about that. Now we have some statements. So Q is going to be some function of P, f of P. In economic terms, what is meant by the statements f of 10 equals 250,000 and f prime of 10 equals negative 28,000. Be sure you put appropriate units in your answers as well. Okay, once again, I'd like you to work this on your own. Come back and check your answer. Press pause now. Well, the first statement, f of 10 equals 250,000, or I might have said q of 10 equals 250,000. That means the quantity is 250,000 when the price is $10 per item. That's actually a unit price. Okay, maybe I should be explicit about that. That's really a unit price. Okay, dollars per item. And there are 200. So if you charge $10 per item, you'll be able to sell 250,000 of these items. Now, what is f prime of 10? Now notice we should have been able to tell that f prime of 10 was negative regardless of whether they told us that or not. Why? Because think of what happens if you increase the x, or the input, okay, or the f prime of x, or p prime of, which is f of prime of x, put the other letters in there, it's q prime of p, right? Now what happens if we increase p by just a little bit? If you increase the price, are you going to sell more items or less items? Well, people are going to probably be willing to buy fewer items, and so you're going to end up selling fewer items. So the total quantity sold is going to be actually less. So that means that the function q of p, or f of x, is a decreasing function. Okay? Well, if it's a decreasing function, then its derivative must be negative. And, of course, it was here. Well, what can we say about the actual number there? 28,000. Well, it means that approximately, if we increase from $10 to $11 per item, okay, then that will result in about 28,000 fewer items sold. So we can say that f of 11 is approximately what? Well, it's about 250,000, but we're going to subtract off that derivative of 28,000, which, what is that? That's still 2, 2, 2, 2, right? Yeah. So you'll be at about 222,000 items sold. Does that mean it's exactly that much? No, we don't know for sure. It could be a little bit higher or lower depending on whether this function is concave up or concave down. If it was linear there, that would be exact. If it's concave up, the actual value would be, let's see, concave up but decreasing. The actual value would be a little higher than this. If it's concave down, it would be a little bit lower than this. But that's our estimate. Try another one. A company's revenue from car sales, we'll call that C, it's going to be measured in thousands of dollars, is a function of advertising expenditures, A, which are also measured in thousands of dollars. Suppose C equals f of A. What does the statement f prime of 100 equals 1.5 mean in practical terms? If that's true, should the company spend slightly more or slightly less than $100,000 on advertising? Once again, you work it out, come back and check your answer in a second or two when you're finished. Press pause now. Well, first of all, note that the units of f prime of A are $1,000 of revenue from car sales per $1,000 of advertising expense, or equivalently dollars of revenue per dollars of ad expense. The thousands sort of cancel out. So when you say f prime of 1,000 is 1.5, that says that increasing advertising expenditures $1 above $100,000 will result in an additional $1.50 in additional revenues. So notice that a $1 investment yields $1.50 in revenue. So if we neglect any other costs associated with this, spending one additional dollar on advertising results in 50 cents, $0.5 profit on the dollar, making it a worthwhile investment to invest slightly more than $100,000 in advertising. You're going to get a good bang for your buck by spending that little bit more on advertising. What if I did exactly the same thing, but this time instead of f prime being 1.5, f prime is 0.8? Well, this time, increasing advertising expenses by $1 results in only an 80-cent increase in extra revenue, so that's a 20-cent decrease in profit. So it's a loss. Okay, we lose some profit. Or at least a lower profit, not necessarily a loss, but a decrease in profit. So we should spend a little less on advertising. Actually, it also goes the other way. It says if we spend $1 less on advertising, we'll lose only 80 cents in revenue, but that will result in increasing our profits by 20 cents. So we should spend less on advertising. Okay, let's look at this next example. Suppose that W of V represents the degree of wind chill when the velocity of wind is V. Interpret the information provided by W prime of 20 equals negative 0.2 and W double prime of 20 is positive. Once again, See if you can figure this out on your own and then come back and check your answer. Press pause now. Okay, well, first of all, let's think about what the units would be. That can kind of help us. So if you're in the United States, appropriate units for wind chill are degrees Fahrenheit and miles per hour for velocity. So the units of W prime of V would be the units of W divided by the units of V, so it would be degrees Fahrenheit per not minutes per hour, miles per hour. Okay, so W prime of 20 equals negative 0.2 means that increasing the wind velocity from 20 miles an hour to 21 miles an hour would result in the wind chill dropping by approximately 0.2 degrees Fahrenheit. So notice that W prime of V is negative, and that makes sense because if we increase the velocity of the wind, that's going to result in a drop in the perceived temperature. It's going to feel colder. Okay? So W prime of 20 is greater than 0 means the graph of W is concave up, W prime is increasing, but also the graph of W was not only is it concave up, it's decreasing. So let's see if I can maybe draw a picture of that. So it's decreasing concave up, so it looks something like this. So is our estimate, so what happens if we go a little further? So let's look at our tangent line to that. Let's say here's the point where we are, velocity of whatever it is, 20 miles an hour, and we increase, blowing this up to emphasize the difference. If you go over 1 from 20 to 21, this amount of drop here on the tangent line is actually the 0.2 degrees Fahrenheit. Okay, and the actual, so it's actually an it's going to drop more than that. I mean, the real thing's not going to drop as much. So what this is saying is, if we knew what the wind chill was right there at that point, then we could subtract 0.2 to approximate what it is here at 21. So this is V is 20 miles per hour. Over here is V equals 21. So delta V is 1. Now, if we start here and go over, notice that the slope is less, so we're going to drop less for the next time. So going from 20 to 21 miles an hour drops about 0.2 degrees Fahrenheit in wind chill, but going from 21 to 22 would be slightly less of a drop, maybe going down maybe 0.1 or something like that, something a little less than the 0.2. Okay, got some more here. Suppose G of T represents the gross national product of a country T years from the beginning of 1985. Suppose that at a particular time the gross national product is increasing, but the economy is starting to lag. What can you say about the signs of G prime of T and G double prime of T? Okay, as before, go ahead and do these on your own. Press pause now. Well, we've been told that G is increasing, but at a decreasing rate. Once G prime is positive, okay, that means that it's increasing, but it's increasing at a decreasing rate, so that G double prime is negative. The economy is the rate of growth of the gross national product. So the economy is the G prime of T. So we're told that when we say the economy is starting to lag, we're saying it's not growing, it's decreasing. The rate of growth is decreasing. So the gross national product may be increasing, but not as fast as it was before. So that makes G double prime negative and G prime positive. And that will stop us for this video, and we have one more in this little series of videos.